Okay, so picture this. You're trying to tune an old radio, but the station you're looking for is broadcasting from the very edge of the universe. You know the signal is there, but it's just buried under layers and layers of static. Well, today we're diving into a piece of research that did something incredible. It found the exact frequency to filter out all that noise, letting us hear some of the universe's most chaotic signals with, get this, perfect clarity.
I mean, this is the fundamental challenge, right? How do you even begin to make perfect predictions for the most chaotic things you can imagine? We're talking about predicting the exact shape of a massive wave in the deep ocean, or the wild path light takes when it zips through a plasma field. For years, our absolute best mathematical tools had this tiny but absolutely crucial flaw, a little bit of static that made all of our predictions fundamentally blurry. So today, we're going to explore the breakthrough that finally cleared up that signal.
All right, so let's really lean into this radio analogy. I want you to think of the universe as just constantly broadcasting these unbelievably complex signals. And to be clear, we're not talking about actual radio waves here. We're talking about the fundamental waves of energy and matter that literally govern everything around us. The whole goal for scientists, then, is to figure out how to tune in and understand them perfectly.
And look, this isn't just some abstract theoretical stuff. The mathematical equation we're going to be digging into today, it's called the HNLS, is used to model very, very real-world things. We're talking about the intricate dance of deep water gravity waves, or the way wave packets focus themselves in superheated plasma, and even the complex behavior of light in nonlinear optics. You see, to really understand these incredibly chaotic systems, you need a very, very special kind of receiver.
So, the big question is, how do scientists tune into all this cosmic chaos? Well, they use a very special kind of mathematical radio. And no, it's not a physical device with knobs and an antenna. It's an equation designed for one purpose, to listen to these incredibly complex wave systems. And here it is, the hyperbolic nonlinear Schrödinger equation, or HNLS for short. This is our Schrödinger radio. Its entire job is to take all those jumbled, chaotic signals we were just talking about and somehow turn them into a clear, predictable picture of how they're going to behave over time. It's an unbelievably powerful tool. Or at least it was supposed to be.
Right. Section 3, a problem of static. You see, here's the catch. For the longest time, this amazing mathematical radio had this nagging, persistent issue. No matter how carefully scientists tried to tune it, there was always a little bit of static in the signal.
And let me tell you, this was not just some minor annoyance. This flaw, which technically is called a derivative loss, meant that our predictions were always, well, fundamentally blurry. Now, a derivative is just a fancy way of talking about the rate of change. You can think of it like the steepness of a wave. So if you're losing that information, it's like trying to look at a picture, but all the sharp edges are gone. It was like a mathematical ghost in the machine that was stopping us from ever seeing things clearly. And this, right here, is the perfect way to see the problem. Over on the left, that's the dream. That's the goal. A sharp, totally crystal clear prediction of how a wave should behave. But on the right, well, that's the reality of what the HNLS equation was actually giving us. A fuzzy, blurry prediction where all the important fine-grained details were just gone. That fuzziness, that was the static.
So, in the world of mathematics, this static, this derivative loss we've been talking about, it has a name. It's called epsilon loss. Now, epsilon is really just a symbol mathematicians use for a super tiny amount, and it represented this small, but absolutely critical error. A loss of information that was literally baked into the very fabric of the equation. This was the source of all that fuzziness.
Okay, section 4, finding the perfect frequency. But what if? What if you could just get rid of that static completely? What if you could find the one perfect frequency that would give you that crystal clear signal? Well, that's exactly what a pair of researchers decided to find out. So let's meet the heroes of our story. In a recent paper, researchers ENGIN and YUZHAO WANG figured it out. They developed a brand new mathematical technique to completely, totally remove the epsilon loss. They essentially found a way to recalibrate that Schrödinger radio and just filter out all that annoying static, for good. Now, of course, science almost never happens in a vacuum, right? And this breakthrough really stood on the shoulders of giants. So first you had the crucial work of Bourgain and Demeter. They were the ones who first really identified this epsilon loss problem. Then you had Killip and Vachon who actually found a way to fix it, but, and this is a big but, only for a much simpler case. So what Bashakolu and Wang did, which was just brilliant, was adapt that method and make it work for the much more complex and chaotic hyperbolic case, the one that had stumped everybody else.
And here you have it, straight from their paper. It says, we derive scale invariant stretch Hartz estimates, thereby removing the epsilon loss of derivative. Okay, I know that sounds like a mouthful, but scale invariant stretch Hartz estimates is just the super technical way of saying they built a new tool that works perfectly no matter how much you zoom in or zoom out on the wave. And the result? They flat out removed the epsilon loss of derivative. It's basically the mathematical way of shouting, we finally got rid of the static.
All right, our final section, a crystal clear signal. So, what does it actually mean to get rid of the static? Well, the impact is, and I'm not exaggerating, profound. It fundamentally changes everything about how reliable our predictions can be.
And this is the result. Epsilon equals 0. Just look at that. The error is gone. The static has been completely, totally silenced. All that precious information that was getting lost before, it's now fully accounted for. It is such a beautifully simple and elegant solution to what was a deeply, deeply complex problem.
You know, there's a name for the grand prize you get for achieving this. It's called local well-posedness. And you can think of it as the ultimate stamp of approval for any mathematical model. It proves 3 really important things. 1, a predictable solution definitely exists. 2, that solution is the only possible one. And 3, tiny little changes at the start won't suddenly cause wildly different results down the line. To go back to our analogy, it means the signal isn't just clear anymore. It's stable, it's reliable, it's trustworthy.
And really, that's the bottom line here. Why does any of this matter? It matters because our models for everything, from deep-sea waves to the physics of plasma, they're not just good anymore. They are now proven to be fundamentally reliable in a way they weren't before. It means our ability to predict some of the most complex systems in the universe has just taken a huge leap forward.
You know, this whole breakthrough is just a perfect example of how something that seems like abstract, pure mathematics can have a massive impact on fine-tuning our understanding of the real physical world. And it leaves us with a really exciting, kind of inspiring question to think about. With this powerful new technique in our toolbox, what other cosmic static in our understanding of the universe are we finally going to be able to tune out next?
All right, today we're diving into a really cool paper. It's one of those breakthroughs that kind of sharpens our whole mathematical view of chaos. We're going to explore some incredible work by ENGIN and YUZHAO WANG. What they did was fix a really nagging, long-standing problem in how we model some of the most complex, wildest wave systems in the entire universe. This is good stuff. So here's how we're going to break this down. I want you to think of this as a bit of a mathematical detective story. First up, we'll meet our main character, Schrödinger's hyperbolic cousin. Then, we'll get into the mystery itself, the epsilon enigma. After that, we'll see the big aha moment, the breakthrough in focus, and look at exactly how they sharpened the equations. And finally, we'll answer the big so what question. Why does all this well-posedness stuff even matter? Let's get into it. Okay, section 1, Schrödinger's hyperbolic cousin. To really get what's going on here, we first need to meet the main character of our story. Now, you've probably heard of the famous Schrödinger equation, right? Well, it turns out it has this wilder, much more chaotic relative. Yeah, the standard Schrödinger equation, I mean, it's an absolute titan of physics. It's pretty much the bedrock of all of quantum mechanics, telling us how quantum systems change over time. It's beautiful, it's elegant, it's powerful, but, and this is a big but, when you start looking at certain really chaotic systems, it's just not the whole story. Okay, now look at this. The difference here is so tiny, but it changes everything. On the left, you've got your standard equation. It uses what's called an elliptic Laplacian operator. Just look at the math, it's all plus signs. That makes it perfect for describing these nice, uniform, isotropic systems. But then, look at its hyperbolic cousin on the right. It just throws in a few minus signs, and that simple, tiny change, wow. It suddenly lets it describe these much more chaotic anisotropic systems, where energy can shoot off in different directions at different speeds. It creates this incredibly complex, almost unpredictable behavior, all from flipping a plus to a minus. Wild, right? And listen, this isn't just some abstract thing for mathematicians to play with. This hyperbolic version, it pops up all over the real world. We're talking about describing the super complex motion of deep water gravity waves, the way wave packets self-focus in scorching hot plasma, even the physics of nonlinear optics. So you can see, really getting a handle on this equation is absolutely key to understanding all these amazing complex phenomena. All right, section 2, the epsilon enigma. So for decades, there's been this problem, a tiny little mathematical flaw that was basically blurring our whole picture of these systems. And this, right here, is the heart of our mystery. Yeah, this wasn't a new problem. People have known about it for years. The brilliant mathematicians Morgaine and Demeter pointed it out really clearly back in 2017. They said, look, the old attempts to nail this equation down, they're flawed. They were all plagued by this thing called a derivative loss, which you see written as n to the power of epsilon. And that little term, that loss, it was making the entire mathematical structure fundamentally unstable. So what is this thing? What exactly is this mathematical villain, this n epsilon loss? You know, the best way to think about it is like a tiny bit of mathematical static, or maybe like some blur in a photo. This derivative loss is basically a loss of information. It's this tiny little error term, this bit of uncertainty that creeps into the calculations and just makes the whole picture of the system way less sharp than we need it to be. And if you look at the old mathematical estimate, you can see the culprit right there. Plain as day. That n to the power of epsilon term. That's the static. That's the source of the blur we've been talking about. And this isn't just some harmless little bit of static, you know? The real problem is, as you try to predict what's going to happen over larger scales or longer periods of time, this n epsilon term just gets worse and worse. It grows and it makes your predictions completely unreliable. It was the one thing stopping mathematicians from proving the equation was truly solid, or what they call well-posed. Okay, section 3, a breakthrough in focus. So, how did this new paper finally clear things up? Well, Bashakolu and Wang, they didn't just find a clue. Oh no, they cracked the entire case wide open. Their approach was just so incredibly clever. They knew the big challenge was this n epsilon loss. So what did they do? They looked at this really powerful tool called the epsilon removal argument. Now, this thing had already been used successfully to clean up the standard, well-behaved Schrödinger equation. The real genius move here was figuring out how to adapt that tool, which, remember, was built for nice, uniform systems, and apply it to the much wilder, much more chaotic hyperbolic case. It's this super sophisticated technique where you basically just keep refining the estimate over and over again, pushing that little epsilon error term smaller and smaller and smaller until, poof, it vanishes completely. And the result? You get these beautiful new estimates that are scale invariant. And what that means is they're sharp and they're clear no matter what scale you're looking at. All right, section 4, sharpening the equations. This is where you can really see how powerful their solution is. Let's just look at the before and after of the equation itself. Okay, so here's the old blurry picture from theorem 1.1. And you can see our villain, that n epsilon term, sitting right there in the middle. It's basically an arbitrary fudge factor. It's like the math is admitting, hey, our tools aren't quite sharp enough, and it was just messing up the precision of the whole estimate. And now, here's the new sharp picture from theorem 1.4. Take a look. Notice what's missing? Yeah, the n epsilon term is gone, completely. In its place, you have this precise, meaningful term that actually depends on the dimensions and the properties of the system itself. The static is gone. The picture is finally in focus. Okay, section 5, why well-posedness matters. So you might be thinking, all right, you removed one tiny symbol from a super long equation. Why is that a big deal? Why should I care? Let's break down what this actually means and why it's so important. It really all comes down to this one crucial concept, well-posedness. In the world of math, a problem is called well-posed if 3 things are true. A solution exists, that solution is unique, and, this is the big one, tiny little changes at the start don't cause wildly different results at the end. In short, it means your model is reliable, it's predictable. Without well-posedness, your equations are basically built on a foundation of sand. So what's the big takeaway here? Well, first off, this breakthrough confirms a major conjecture from Morgaine and Demeter, which is huge. It gives mathematicians a ton of confidence that they're heading in the right direction. More importantly, it finally establishes a solid, reliable foundation for the hyperbolic Schrödinger equation, and that unlocks the ability to study all those crazy systems, like deep water waves, with way more precision than ever before. What they've really done is given all of us a much sharper lens to look at the universe of complex systems. And that, of course, leaves us with a pretty fascinating question to think about, doesn't it? Now that we have this much clearer view of these chaotic systems, now that we've finally removed the static that was blurring our predictions, what new discoveries are we going to be able to predict? What new phenomena will we finally be able to see clearly for the first time? Today, we're diving into a fascinating new paper that sharpens our focus on some of the most chaotic, powerful systems in the known universe. We're going to see how mathematicians took on a long-standing problem, a kind of blur in their equations, and finally wiped it clean. And the result? A much clearer, more reliable picture of everything from monstrous deep ocean waves to superheated plasma. Okay, so let's just start with this question. I mean, think about it for a second. Deep ocean waves and superheated plasma. You've got the crushing, icy cold of the abyss on one hand, and the searing, unimaginable heat of, say, a star's atmosphere on the other. They seem like polar opposites, right? But it turns out, in the world of physics and math, they are secretly speaking the same language. And that shared language, well, it's an equation, a very specific kind of equation. Now, many of you have probably heard of the Schrödinger equation from quantum mechanics, the one that governs the weird, fuzzy world of particles. But for these huge, chaotic systems, scientists need a totally different version of it, a version that's built from the ground up to handle opposing forces. So at the very core of this difference is a mathematical engine called the Laplacian. For most systems, things that are relatively smooth and predictable, you use the standard or elliptic version. You can think of it as all the forces just adding up, working together. But for chaos, for systems with a constant tug of war happening inside them, you need what's called a hyperbolic Laplacian. And here's the key. This version allows you to subtract forces. That one little change, from adding to subtracting, completely rewrites the rules for how the system evolves. And that brings us to the star of today's show, the hyperbolic nonlinear Schrödinger equation, HNLS for short. This is it. This is the mathematical script that describes the wild dance of plasma and deep-sea waves. It's our best shot at taming that chaos. But for a very long time, there was a really big problem lurking inside of it. So here's the thing. It's one thing to have a fancy equation that looks good on paper, but it's another thing entirely to know if you can actually trust it, Is it reliable? And for years, that was the big, nagging question about the HNLS model. Let's dig into why.
In math and physics, the absolute gold standard for any model is a concept called well-posedness. It sounds complicated, but the idea is actually pretty simple. A model is well-posed if a tiny little nudge at the beginning only causes a tiny little change at the end. If you tweak the starting wave height by a millimeter and the model predicts a tsunami the size of Mount Everest, well, that model isn't stable and it's not very useful for predicting anything.
To get that well-posed badge of honor, a model has to clear 3 critical hurdles. First, a solution actually has to exist, which you'd be surprised isn't always a given. Second, there can only be one unique solution for any starting point. No multiple personalities allowed. And third, it has to be stable. That's our small nudge, small change rule. Only if a model passes all 3 tests can we really, truly trust what it's telling us. And for the HNLS, that third step, proving stability, was a massive headache. Why? Because the best tool mathematicians had to do the job was, well, for lack of a better word, it was blurry. So this specific tool is called a Strichardt's estimate, and the leading version for these kinds of problems, created by the brilliant mathematicians Bourgain and Demeter, had this tiny, incredibly frustrating flaw. It was a little term in the math that looked like n to the power of epsilon. Now, you can think of n as your zoom level, how closely you're looking at the system. The problem was, the more you zoomed in, the more you tried to see the fine details, the worse this epsilon loss got. It was literally like a smudge on a camera lens that got bigger and blurrier the harder you tried to focus.
And let me be clear, this wasn't some tiny, obscure issue that only a few people cared about. This was a major, open problem in the field. In fact, the very people who developed the tool, Bourgain and Demeter, they suspected that this blur wasn't fundamental. They conjectured that it could be removed. But for years, nobody could figure out how. The problem just sat there, unsolved.
Until now. And this, of course, is where our new paper comes in. This is where the work of ENGIN and YUZHAO WANG enters the story, because they finally found a way to wipe that smudge right off the lens. What they did was brilliant. They took a clever technique from a completely different area of math and figured out how to apply it here. And with this new method, that annoying n to the epsilon term, it's just gone. Wiped out completely, the mathematical blur has vanished. The new tool is what's called sharp and scale invariant, which is really just a fancy way of saying it works perfectly with crystal clarity no matter how much you zoom in. The lens is finally in focus.
Okay, so a cleaner equation is awesome news for mathematicians. But what about for the rest of us? Why does this matter? It matters because it means we can finally have real confidence in what these crucial physics models are telling us about our world. The impact of this sharper tool is immediate, and it's powerful. It finally proves that the HNLS model is reliable. It's well posed for the complex 3D and 4D systems that we actually see in nature. It puts our models for things like plasma and deep water waves on rock-solid ground. It means we can now trust calculations that were previously, honestly, right on the razor's edge of uncertainty.
So, let's just pause for a second and appreciate the journey here. We started with a simple question about what waves and plasma have in common. That led us down a rabbit hole into a deep mathematical problem, and out the other side to a genuine breakthrough that literally sharpens our view of reality.
The difference really is just night and day. We've gone from a blurry tool that had a limited scope and left us with uncertainty to a new, sharp tool that lets us study way more complex problems and gives us high confidence in our models of chaotic systems. It is just a perfect, beautiful example of how progress in really abstract mathematics can have a huge real-world impact.
And that kind of leaves us with one last, really exciting thought. This breakthrough cleaned one very, very important lens. But it just makes you wonder, doesn't it? What other parts of our universe, from climate science to cosmology, are we currently looking at through a haze? What other complex systems are just out there, waiting for the right person, the right idea, to come along and finally sharpen the focus?